The universe runs on a single cosmic speed limit. Change it by just 1%, and you disappear in ways physics can't even describe. Every atom in your body, every star in the sky, every thought in your mind exists because light travels at one exact speed. Not faster, not slower, exactly what it is. What if it changed tomorrow just 1%? Today, I'm showing you why the speed of light is the most terrifyingly important thing in existence, and why the universe hangs by this single, impossibly precise thread. If you're fascinated by these cosmic mysteries and want to explore more mind-blowing science, make sure to subscribe to this channel and give a thumbs up. And here's a question for you. If you could change one fundamental constant of the universe without destroying it, which one would you choose? And let me know in the comments down below. I will choose the most creative answer. Now let's begin. The speed of light, 300,000 kilometers per second, is not just how fast light travels, it's woven into the very equations that describe existence. Change that speed, and you change the fundamental relationship between matter and energy throughout the cosmos. Recent observations from the Event Horizon Telescope, which gave us our first image of a black hole in 2019, revealed something profound. The way light bends around massive objects, the way time dilates near black holes, the very structure of space-time itself. All of it depends on light speed being exactly what it is. The data from Sagittarius A star, our galaxy's central black hole, shows gravitational effects that match Einstein's predictions to incredible precision. But those predictions assume light speed is constant. Change it, and black holes might not even be possible. Start with what would happen at the atomic level if light speed increased by just 1%. Atoms are held together by electromagnetic forces, and these forces propagate at light speed. The Rydberg constant, which determines the energy levels in atoms, depends on light speed to the fourth power. A 1% increase in light speed means about a 4% change in atomic energy levels. Electrons would suddenly find themselves in the wrong orbits. They'd either crash into the nucleus or fly away entirely. Every atom in your body, every atom in Earth, every atom in the universe would become unstable simultaneously. The NIST atomic clocks in Boulder, Colorado, which keep time so precisely they won't lose a second in 300 million years, have shown us something remarkable. The electromagnetic forces holding atoms together are perfectly balanced with the other fundamental forces. This balance depends critically on light speed. Recent experiments with ytterbium atomic clocks have measured these forces to unprecedented precision, change light speed, and this delicate balance shatters like crystal hitting concrete. But it gets worse, much worse. The strong nuclear force that holds protons and neutrons together in atomic nuclei also depends on light speed through quantum field theory. The residual strong force, mediated by pions traveling at significant fractions of light speed, would change dramatically. Nuclei that are stable now would become radioactive. Others might collapse. The careful balance between the strong force and electromagnetic repulsion in nuclei would fail catastrophically. Data from the Large Hadron Collider at CERN has given us incredible insights into these nuclear forces. When protons collide at 99.9999% of light speed, we see the fundamental forces at work. The Higgs boson discovery in 2012 showed us how particles acquire mass through their interaction with the Higgs field. But the Higgs mechanism itself depends on light speed. Change c and particle masses throughout the universe would shift, destroying the delicate balance that makes atoms possible. Consider what this means for stars. Our Sun fuses hydrogen into helium through a precise chain of nuclear reactions. The proton-proton chain that powers the Sun depends on quantum tunneling, where particles overcome energy barriers they classically shouldn't be able to cross. The probability of tunneling depends exponentially on particle velocities relative to light speed. Increase light speed, and fusion rates explode. Decrease it, and fusion might stop entirely. The Solar Dynamics Observatory has been watching our Sun continuously since 2010, measuring the delicate balance between gravitational collapse and fusion pressure. This balance, called hydrostatic equilibrium, keeps stars stable for billions of years, change light speed, and this balance fails instantly. Stars would either explode in seconds or collapse into black holes depending on which direction light speed changed. Recent data from the Gaia Space Telescope, which has mapped over 1 billion stars in our galaxy, shows us the incredible diversity of stellar types: red dwarfs, yellow stars like our Sun, blue giants. Each represents a different balance point between gravity and fusion. All these balance points would shift if light speed changed. The entire Hertzsprung-Russell diagram, our map of stellar evolution, would be rewritten in an instant. But here's where it gets truly cosmic. The expansion of the universe itself is intimately connected to light speed. Observations from Type Ia supernovae, which won the 2011 Nobel Prize in Physics, showed us the universe's expansion is accelerating. This acceleration is described by the Friedmann equations, which include light speed as a fundamental parameter. Change c, and you change how space itself expands. The Planck satellite mapped the cosmic microwave background, the afterglow of the Big Bang, with extraordinary precision. This ancient light, traveling for 13.8 billion years, carries information about the early universe. The patterns we see, the tiny temperature fluctuations that seeded galaxy formation, depend on the relationship between matter, radiation, and the speed of light in the early cosmos. Alter light speed, and the entire history of the universe changes. Think about this: the cosmic microwave background temperature is 2.725 Kelvin. This precise value results from the universe's expansion over billions of years, with photons redshifting as space stretches. The redshift formula directly involves light speed. Change c, and the CMB temperature changes, altering the thermal history of the universe. Galaxies might never form, or they might form too quickly and burn out. Gravitational waves detected by LIGO and Virgo observatories travel at light speed. The 2017 detection of both gravitational waves and light from colliding neutron stars proved this conclusively. These ripples in space-time carry energy away from accelerating masses. Change light speed, and gravitational waves would travel at different speeds, fundamentally altering how massive objects interact across cosmic distances. The implications cascade through every scale of existence. Quantum mechanics and general relativity, the two pillars of modern physics, both incorporate light speed fundamentally. The uncertainty principle, which governs the quantum world, relates position and momentum uncertainties through Planck's constant, but Planck's constant itself is defined using light speed. Change c, and the quantum fuzziness that allows atoms to exist would shift dramatically. Particles might become so uncertain they couldn't form stable matter, or so certain they'd violate the laws of thermodynamics. Recent experiments at the National Institute of Standards and Technology have pushed quantum measurement to extraordinary limits. Using trapped ions cooled to near absolute zero, scientists have observed quantum superposition states that exist for mere microseconds. These delicate quantum states depend on the precise relationship between electromagnetic forces and quantum uncertainty. Alter light speed, and these states would either collapse instantly or become so stable that quantum mechanics itself would break down. Let me paint you a picture of what would actually happen in the first nanosecond if light speed increased. Electromagnetic signals between atoms would arrive faster than expected. Chemical bonds, which rely on electron sharing between atoms, would strengthen or weaken unpredictably. Water molecules would change their angle. DNA would unwind. Proteins would unfold. The molecular machinery of life, fine-tuned over 4 billion years of evolution, would jam like gears filled with sand. The Atacama Large Millimeter Array in Chile has revealed something profound about cosmic chemistry. Complex organic molecules exist in interstellar clouds, forming through reactions that depend precisely on electromagnetic forces. These cosmic chemical factories create the building blocks of life, but only because reaction rates are perfectly balanced with radiation pressure from nearby stars. Change light speed, and this cosmic chemistry set stops working. The universe would become chemically sterile. But wait, it gets even stranger. Time itself would break. Special relativity tells us that time and space are interwoven through light speed. The Lorentz transformation, which describes how time dilates and space contracts for moving objects, has c at its heart. GPS satellites orbiting Earth must account for time dilation effects of just nanoseconds. Change light speed, and every GPS calculation fails. But that's trivial compared to what happens to causality itself. The advanced LIGO detectors can measure distance changes smaller than a proton's width. This incredible precision has revealed how space-time itself ripples and flexes. These measurements confirm that space-time has specific elastic properties, like a cosmic fabric with particular stiffness. This stiffness is set by light speed. Change c, and space-time becomes either too rigid for gravity to work, or so flexible that space itself would tear apart. Consider black holes, those cosmic monsters where gravity overwhelms everything else. The event horizon, the point of no return, exists where escape velocity equals light speed. The Schwarzschild radius is directly proportional to mass, but inversely proportional to c squared. Double light speed, and every black hole's event horizon shrinks to 1/4 its current size. Massive amounts of previously trapped matter and energy would suddenly escape, turning every black hole into a cosmic bomb. Data from the Chandra X-ray Observatory shows us matter spiraling into black holes, heating to millions of degrees and emitting X-rays just before crossing the event horizon. This process, called accretion, powers the brightest objects in the universe, quasars. Change light speed and accretion physics changes completely. Quasars might shut off instantly or become so bright they'd sterilize entire galaxies with radiation. The cosmic web itself would unravel. Dark matter, which we detect through gravitational effects on visible matter, interacts with normal matter primarily through gravity. The Hubble Space Telescope and now the James Webb Space Telescope have mapped dark matter's distribution by observing gravitational lensing, how massive objects bend light. This bending depends on the relationship between gravity and light speed. Alter c, and dark matter's gravitational effects would change, potentially destabilizing every galaxy in the universe. Recent observations of galaxy cluster collisions like the famous Bullet Cluster show dark matter and normal matter separating during cosmic crashes. This separation happens because dark matter only interacts gravitationally, while normal matter experiences electromagnetic forces too. Change light speed, and the balance between these interactions shifts. Galaxies might fly apart or collapse depending on which way c changes. Let's talk about something even more fundamental, the vacuum of space itself. Quantum field theory tells us empty space seethes with virtual particles popping into existence and annihilating. This vacuum energy depends critically on light speed through the uncertainty principle. Change c and vacuum energy density changes. The Casimir effect, measured precisely in laboratories, proves vacuum energy is real. Alter light speed significantly and vacuum energy might tear space apart or collapse it entirely. The Parker Solar Probe, humanity's first spacecraft to touch the Sun's corona, has revealed the incredible complexity of stellar atmospheres. Solar wind accelerates away from the Sun through magnetic field interactions that propagate at light speed. Change c, and magnetic fields would propagate differently. The solar wind might become a devastating blast or dwindle to nothing. Earth's protective magnetosphere, our shield against cosmic radiation, would fail to deflect changed solar wind properly. Pulsars, those lighthouses of the cosmos spinning hundreds of times per second, would face an identity crisis. The Arecibo Observatory, before its tragic collapse, and now the FAST telescope in China, have timed pulsar rotations to incredible precision. These neutron stars maintain stability through a balance between gravity, nuclear forces, and electromagnetic radiation. The radiation is emitted at light speed from their magnetic poles. Change C and pulsars would either spin themselves apart or collapse into black holes. Consider cosmic rays, those high-energy particles that bombard Earth constantly. The Pierre Auger Observatory in Argentina detects the highest energy cosmic rays ever observed, particles with energies equivalent to a baseball thrown at 90 kilometers per hour, compressed into a single proton. These particles travel at speeds so close to light speed that changing CE even slightly would dramatically alter their behavior. They might become harmless or so energetic they destroy DNA on contact. The very notion of now across the universe would shatter. Simultaneity, as Einstein showed us, depends on light speed. Events that appear simultaneous to one observer might not be to another moving relative to them. This relativity of simultaneity keeps causality intact. Effects never precede causes. Change light speed, and the cosmic speed limit that preserves causality changes. Parts of the universe might experience effect before cause, creating paradoxes that would unravel logic itself. The electromagnetic spectrum itself would shift in ways that boggle the mind. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, all are electromagnetic radiation distinguished only by wavelength and frequency. The relationship between wavelength, frequency, and speed is fundamental. Wavelength times frequency equals c. Change light speed, and every form of electromagnetic radiation changes character. Radio telescopes like the Very Large Array in New Mexico would suddenly receive signals at wrong frequencies. The cosmic symphony would shift into new keys we can't even imagine. Recent discoveries from the ALMA telescope have shown us stellar nurseries where baby stars form from collapsing gas clouds. The process depends on a delicate balance between gravity pulling inward and radiation pressure pushing outward. Infrared light from warming dust grains provides just enough pressure to slow collapse, allowing planets to form. Change light speed, and radiation pressure changes. Stars might form too quickly, burning out before planets could develop, or so slowly that the universe would still be dark. This brings us to one of physics' most intriguing questions. Could we ever travel faster than light? Speaking of which, if you're fascinated by the possibilities and limitations of faster-than-light travel, check out my video called Light Speed versus Warp Speed. Which one really wins? Where we dive deep into the physics of science fiction's favorite propulsion system and whether bending space-time could actually let us cheat the cosmic speed limit. The link is in the description below and pinned on the comments. Now back to our cosmic catastrophe. The fine structure constant, perhaps the most mysterious number in physics, would change if light speed changed. This dimensionless constant, approximately 1/137, appears everywhere in quantum mechanics and determines the strength of electromagnetic interactions. It's built from fundamental constants, including light speed. Change C and the fine structure constant changes, altering how electrons orbit nuclei, how atoms bond, how chemistry works. Life as we know it exists only because this constant has precisely the value it does. Experiments at the relativistic heavy ion collider have recreated conditions from microseconds after the Big Bang. Quark-gluon plasma, a state of matter where quarks and gluons flow freely, existed before atoms could form. The transition from this plasma to normal matter depended critically on the cooling rate of the universe, which relates to light speed through cosmic expansion. Change c in the early universe and atoms might never have formed at all. We'd have a cosmos of eternal plasma with no stars, no planets, no possibility of life. The James Webb Space Telescope has peered deeper into space and time than ever before, seeing galaxies as they were over 13 billion years ago. These observations reveal something profound. The fundamental constants appear unchanged across cosmic history. The spectral lines from ancient galaxies match those we see in Earth laboratories. This constancy of physics made our existence possible, but if light speed could change, this cosmic stability would shatter. Neutrinos, those ghostly particles that barely interact with matter, would behave completely differently. The Super Kamiokande detector in Japan and IceCube at the South Pole have caught neutrinos from the Sun, supernovae, and distant cosmic accelerators. These particles travel at nearly light speed, oscillating between different types as they fly. The oscillation depends on their mass and speed relative to c. Change, light speed, and neutrino oscillations would change, potentially making them strongly interacting. The trillions of neutrinos passing through you right now might suddenly become deadly radiation. Let's dive into what would happen to electricity and magnetism. Maxwell's equations, the mathematical poetry that describes all electromagnetic phenomena, have light speed built into their very structure. The permittivity and permeability of free space multiply together with c squared. Change light speed, and you must change one or both of these fundamental properties of space. Electric fields might become stronger or weaker. Magnets might barely work or become impossibly powerful. Your smartphone would instantly become a brick. The semiconductors in computer chips rely on precise control of electron movement through electric fields. Change how quickly these fields propagate, and every calculation fails. But it's worse than just technology failing. Your nervous system is electrical. Neurons fire by moving ions across membranes, creating electrical pulses that travel along axons. These biological electrical systems evolved assuming specific propagation speeds. Change c and thoughts themselves might travel too fast or too slow for consciousness to emerge. The Voyager spacecraft, humanity's most distant ambassadors now in interstellar space, communicate with Earth using radio waves. At their current distance of over 23 billion kilometers, signals take nearly 22 hours to reach us. Change light speed, and not only would communication times change, but the very nature of electromagnetic communication would alter. Antenna theory, signal propagation, everything we know about sending information through space would need rewriting. Recent gravitational wave detections have revealed something beautiful. When black holes merge, they ring like bells, emitting gravitational waves at specific frequencies determined by their mass and spin. This ring-down follows precise mathematical patterns predicted by general relativity. Change light speed, and these patterns would shift. The cosmic symphony of merging black holes would play in different tones, if it played at all. The cosmic distance ladder, our method for measuring the universe's vast scales, would collapse. We measure nearby stars using parallax, farther stars using their intrinsic brightness, distant galaxies using type Ia supernovae, and the farthest reaches using redshift. Each rung of this ladder depends on light behaving consistently. Change c, and every cosmic distance measurement becomes wrong. The universe might be larger or smaller than we think, older or younger, more crowded or more empty. Photosynthesis, the process that feeds almost all life on Earth, would fail catastrophically. Plants capture photons and use their energy to split water and create sugars. The efficiency of this process depends on photons having specific energies, which relate to their frequency and thus to light speed. Change C, and sunlight might become useless to plants, or so energetic it would destroy chlorophyll molecules. The green world would turn brown in days. The Heisenberg uncertainty principle sets fundamental limits on what we can know. You cannot simultaneously know a particle's exact position and momentum. This isn't just measurement difficulty, it's built into reality's fabric. The uncertainty relation involves Planck's constant, which relates to light speed. Change C, and uncertainty itself changes. Atoms might become so uncertain they dissolve into probability clouds, or so certain that quantum mechanics ceases to function. Dark energy, that mysterious force accelerating cosmic expansion, would respond unpredictably to changing light speed. The Supernova Cosmology Project and High-Z Supernova Search Team discovered cosmic acceleration by observing distant supernovae. These observations assume light speed has been constant throughout cosmic history. If C could change, dark energy might not exist at all. The apparent acceleration could be an illusion caused by evolving light speed. The Anthropic principle, the observation that the universe seems fine-tuned for life, becomes even more mysterious when we consider light speed. Scientists at the Institute for Advanced Study have calculated that changing fundamental constants by even tiny amounts would create sterile universes. Light speed sits at the center of these calculations. It's not just one number among many, it's the kingpin that, if moved, causes all other cosmic dominoes to fall. Recent observations from the Keck Observatory in Hawaii have measured the cosmic web structure using the light from distant quasars. As this light passes through intergalactic gas clouds, it creates absorption lines, a cosmic barcode telling us about matter between us and the quasar. These measurements show that physics works the same way across billions of light years and billions of years, but change, light speed, and this cosmic consistency vanishes. Different regions of space might have different physics, creating a patchwork universe where natural laws vary from place to place. Imagine water for a moment. Its unique properties, expanding when it freezes, dissolving more substances than any other liquid, having high surface tension, all stem from electromagnetic forces between molecules. The hydrogen bonds that give water its magic depend on electric charges interacting at light speed, change C, and water might not be liquid at room temperature. Oceans could instantly freeze or boil. Blood, which is mostly water, would cease to function as a biological transport system. The Large Hadron Collider has shown us that mass itself emerges from energy through interactions with the Higgs field. The famous equation E equals mc squared isn't just about converting matter to energy in nuclear reactions. It tells us that mass is energy, frozen into particles by interactions happening at light speed. Change C, and every particle's mass changes. Electrons might become heavier than protons. Matter as we know it would restructure itself at the most fundamental level. Consider what happens to radioactive decay. Carbon-14 dating, which archaeologists use to date ancient artifacts, depends on radioactive carbon decaying at a precise rate. This rate is set by quantum mechanics and the weak nuclear force, both involving light speed fundamentally. Change C and decay rates change. Elements that are stable might become radioactive. Radioactive elements might become stable. The natural nuclear reactor that ran for millions of years in Oklo, Gabon, could never have existed with different physics. The Fermi Gamma-Ray Space Telescope has detected gamma-ray bursts, the universe's most powerful explosions since the Big Bang. These cosmic fireworks occur when massive stars collapse or neutron stars collide, releasing more energy in seconds than our Sun will produce in its entire lifetime. The physics of these explosions depends critically on how quickly gravity and electromagnetic forces propagate. Changing light speed and gamma-ray bursts might be impossible, or they might be so common that life could never evolve anywhere in the universe. Time dilation near massive objects confirmed by GPS satellites that must correct Einstein's predictions would change dramatically. Currently, time passes slightly faster on your head than your feet due to Earth's gravity, a difference of about 1 nanosecond per year per meter of height. Change light speed, and this gravitational time dilation would shift. Time might flow so differently at different altitudes that synchronized civilization would be impossible. Let's talk about entropy and the arrow of time. The second law of thermodynamics says entropy always increases, giving time its direction. But entropy increase is really about information spreading through space, and information can't travel faster than light. Change c, and you change how quickly systems can reach equilibrium. The universe might age faster or slower. The heat death of the cosmos, that final state of maximum entropy, might arrive in billions of years or billions of centuries. The LIGO and Virgo collaborations have detected dozens of gravitational wave events, each carrying information about cosmic catastrophes. These ripples in space-time travel at exactly light speed. We've measured this precisely by comparing gravitational waves and electromagnetic signals from the same events. If light speed changed but gravitational waves didn't, or vice versa, causality would break. You could receive gravitational news of a supernova before the star actually exploded from its own perspective. Quantum entanglement, what Einstein called spooky action at a distance, seems to transcend light speed limits. When entangled particles are measured, they instantly correlate regardless of separation. But no information actually travels faster than light in this process. Change c, and the delicate relationship between entanglement and relativity would shatter. Quantum mechanics and relativity, already in tension, might become fundamentally incompatible. The cosmic microwave background's near-perfect uniformity tells us the early universe reached thermal equilibrium. But regions now separated by billions of light-years were never in causal contact if light speed has always been constant. This horizon problem puzzles cosmologists. Inflation theory solves it by proposing rapid expansion, but what if light speed was different in the early universe? Some theories suggest c might have been infinite at the Big Bang, allowing instant communication across all space before slowing to its current value. Recent discoveries of gravitational lensing by galaxy clusters have revealed dark matter's distribution in unprecedented detail. The Hubble Frontier Fields program uses massive galaxy clusters as cosmic telescopes, magnifying distant galaxies behind them. This lensing depends on light following curved paths through warped spacetime. Change light speed, and these cosmic lenses would focus differently. We might see entirely different views of the distant universe, or the lensing might become so extreme that space would appear shattered like a broken mirror. The Breakthrough Listen project searches for extraterrestrial intelligence by monitoring radio signals from space. But communication between civilizations assumes physics works the same everywhere. If light speed could vary, different regions of the universe might be forever isolated, not by distance, but by incompatible physics. Imagine trying to send a message when the very nature of electromagnetic waves changes between sender and receiver. Solar sails, like the Planetary Society's Light Sail project, use radiation pressure for propulsion. Photons carry momentum despite having no mass, pushing on reflective surfaces. This momentum equals energy divided by c, change light speed, and radiation pressure changes. Solar sails might become impossibly efficient or completely useless. The concept of using light for space travel would need complete reimagining. The quantum vacuum isn't empty but seethes with virtual particles appearing and disappearing. The Lamb shift in hydrogen atoms, measured to extraordinary precision, proves these vacuum fluctuations affect real particles. The energy density of vacuum fluctuations involves light speed to the fourth power. Change C even slightly, and vacuum energy could dominate everything else, either tearing space apart or crushing it into nothing. The development of life itself required billions of years of cosmic stability. The Miller-Urey experiment showed that organic molecules could form from simple chemicals and energy, but this process needs consistent physical laws over geological time. Change light speed during Earth's history, and evolution's delicate chemical dance would stumble. DNA replication depends on hydrogen bonds forming and breaking at precise rates. Protein folding requires electromagnetic forces to guide amino acid chains into functional shapes. Alter C, and 4 billion years of evolution unravels in microseconds. Recent studies using the Atacama Cosmology Telescope have mapped the universe's structure at different epochs. These observations show that galaxies formed through gravitational instability, tiny density fluctuations in the early universe, grew over billions of years into the cosmic web we see today. This growth rate depends on the balance between gravity's pull and radiation's push. Change light speed, and galaxies might never form, or they might collapse too quickly into universe-spanning black holes. The Parker Solar Probe has revealed that our Sun's magnetic field undergoes constant reconnection events, where magnetic field lines break and reconnect in new configurations. These reconnections release enormous energy, driving solar flares and coronal mass ejections. The reconnection speed is limited by how fast information can propagate through the plasma, essentially a fraction of light speed. Change C and solar magnetic activity could become either boringly quiet or violently explosive. Let me share something that keeps physicists awake at night: the hierarchy problem. Gravity is absurdly weak compared to other forces. A tiny magnet can lift a paperclip against the entire Earth's gravitational pull. This weakness might relate to light speed through extra dimensions or other exotic physics. Change C and the balance between forces could shift dramatically. Gravity might become as strong as electromagnetism, making planets impossible, or so weak that galaxies would dissipate into isolated stars. The most precise measurement ever made by humans involves light speed. The NIST F2 atomic clock measures time to an accuracy of 1 second in 300 million years. This precision depends on cesium atoms transitioning between energy states at exactly 9,192,631,770 oscillations per second. This frequency relates directly to light speed through quantum mechanics. Change C and time itself becomes unmeasurable. Observations from the South Pole Telescope have detected the Sunyaev-Zeldovich effect, cosmic microwave background photons gaining energy by passing through hot galaxy clusters. This effect lets us weigh galaxy clusters and map hot gas in the universe. The energy boost depends on photons traveling at exactly c. Change light speed, and our entire understanding of cosmic structure would need revision. Galaxy clusters might be heavier or lighter than we think. Dark matter might be more or less abundant. The concept of a light cone, the region of space-time that can causally affect or be affected by an event, structures everything in relativity. Your future light cone contains everything you could possibly influence. Your past light cone contains everything that could have influenced you. Change light speed, and these cones expand or contract. With faster light, you could affect more of the universe. With slower light, you'd be more isolated. The very notion of cause and effect would geometrically restructure. Recent discoveries by the IceCube Neutrino Observatory have detected high-energy neutrinos from a blazar 4 billion light-years away. These nearly massless particles traveled for billions of years to reach us, barely interacting with matter along the way. Their journey depends on their speed being just slightly less than c due to their tiny mass. Change light speed, and neutrinos might become trapped by gravity or zoom away so fast they'd never interact with detectors. The Chandrasekhar limit, about 1.4 times our Sun's mass, determines when white dwarf stars explode as type Ia supernovae. This limit emerges from the balance between electron degeneracy pressure and gravity, involving both quantum mechanics and relativity. Light speed appears in the equations determining this critical mass. Change c and the Chandrasekhar limit shifts. Stars that should explode might not. Stars that shouldn't explode might. Our cosmic distance measurements, which rely on type Ia supernovae as standard candles, would become meaningless. Consider the bizarre world of quantum tunneling. Particles can pass through barriers they shouldn't classically be able to cross. This isn't science fiction, it's how the sun shines, how radioactive decay works, and how scanning tunneling microscopes operate. The tunneling probability depends exponentially on the barrier width and particle energy relative to mc squared. Change light speed, and tunneling rates throughout the universe would shift. The sun might burn out instantly or last forever. The cosmic neutrino background, relic neutrinos from just seconds after the Big Bang, fills the universe with about 300 neutrinos per cubic centimeter. We haven't detected these directly yet, they're too low energy, but they must exist based on Big Bang nucleosynthesis. These ghostly particles have been traveling at nearly light speed for 13.8 billion years, change c during cosmic history, and these neutrinos would carry that information, providing a fossil record of physics itself changing. NASA's Transiting Exoplanet Survey satellite has discovered thousands of planets orbiting other stars. These discoveries rely on detecting tiny brightness dips as planets pass in front of their stars. The timing of these transits depends on light traveling at constant speed from star to telescope. Change light speed, and every exoplanet orbit would need recalculation. Planets we think are in habitable zones might actually be frozen or fried. The strong CP problem in particle physics asks why the strong nuclear force preserves certain symmetries. The solution might involve axions, hypothetical particles that could constitute dark matter. Axion properties depend critically on the relationship between strong force dynamics and electromagnetic interactions. Change light speed, and axions might become detectable or disappear entirely. Dark matter itself might fundamentally change character. Plasma physics, which governs most visible matter in the universe, would transform completely. Stars are plasma. The solar wind is plasma. Even interstellar space contains thin plasma. Plasma oscillations, Alf-Venn waves, and magnetohydrodynamic phenomena all depend on the relationship between charged particle motion and electromagnetic field propagation. Change c, and stars might not be able to maintain stable fusion. The solar wind might strip away planetary atmospheres or fail to reach planets at all. The edge of the observable universe currently sits about 46 billion light-years away, not 13.8 billion, because space itself has expanded while light traveled toward us. This cosmic horizon depends directly on light speed and the universe's expansion history. Change c, and the observable universe would shrink or grow. We might see galaxies that are currently hidden beyond our horizon, or lose sight of galaxies we can currently observe. The discovery of fast radio bursts, millisecond pulses of radio waves from distant galaxies, has opened a new window into extreme physics. The CHIME telescope in Canada detects several of these mysterious signals daily. Their dispersion through intergalactic plasma tells us about matter between galaxies. This dispersion measure depends on radio waves traveling at exactly c through different media, change light speed, and these cosmic messages would arrive garbled or not at all. We might be missing entire categories of cosmic phenomena simply because their signals travel at speeds we can't detect. Black hole thermodynamics, discovered by Stephen Hawking, reveals that black holes emit radiation and eventually evaporate. The temperature of this Hawking radiation inversely relates to the black hole's mass through equations involving light speed. Change c, and black holes might evaporate instantly in explosive bursts or become absolutely eternal, never losing mass. The information paradox, whether information falling into black holes is destroyed, would take on entirely new dimensions. The Vera Rubin Observatory, currently beginning its survey of the entire southern sky, will detect millions of asteroids, supernovae, and other transient events. Its ability to spot moving objects depends on comparing images taken at different times, assuming light travels at constant speed. Change c, and every trajectory calculation fails. An asteroid we think will miss Earth might be on a collision course, or vice versa. Our ability to predict cosmic threats would vanish. Let's delve into something truly mind-bending: the relationship between light speed and consciousness itself. Neural signals propagate at speeds much slower than light, typically 1 to 100 meters per second. But the electromagnetic fields generated by neural activity propagate at light speed. Some theories of consciousness propose that these field effects are crucial for binding distributed brain activity into unified experience. Change c, and the timing of neural field interactions would shift. Consciousness might speed up, slow down, or fragment entirely. Recent experiments with Bose-Einstein condensates, ultra-cold atoms that act as single quantum objects, have created conditions where light effectively slows to walking speed or stops entirely. This isn't changing c itself, but changing how light propagates through matter. These experiments reveal how intimately light speed relates to the quantum properties of matter. If c itself changed, these exotic states of matter might become impossible or spontaneously form everywhere. The cosmic lithium problem illustrates how precisely balanced our universe is. Big Bang nucleosynthesis predicts how much hydrogen, helium, and lithium formed in the first minutes after the Big Bang. Observations match predictions perfectly for hydrogen and helium, but we see only about 1/3 the expected lithium. This discrepancy might hint at new physics, possibly involving variations in fundamental constants. Change light speed in the early universe, and element formation would follow completely different patterns. The universe might be pure hydrogen, pure iron, or filled with elements that can't exist under current physics. Gamma-ray astronomy has revealed that the universe is more transparent to high-energy photons than expected. TeV photons from distant blazars should interact with infrared background light, creating electron-positron pairs. But we see more high-energy gamma rays than predicted. This might indicate new physics, or that light speed varies slightly with energy. If c isn't perfectly constant even now, our entire cosmological model might need revision. The magnetic monopole problem asks why we've never found isolated magnetic charges, despite many theories predicting them. Maxwell's equations become beautifully symmetric if magnetic monopoles exist, but this symmetry involves light speed fundamentally. Change c and magnetic monopoles might spontaneously appear throughout the universe, or electric charge itself might become impossible. The electromagnetic force could split into separate electric and magnetic forces with different propagation speeds. Observations of binary pulsars, particularly the Hulse-Taylor system, have confirmed gravitational wave emission to extraordinary precision. These systems lose energy exactly as Einstein predicted, spiraling inward as gravitational waves carry energy away at light speed. Change c, and these cosmic clocks would tick differently. The match between theory and observation that earned the 1993 Nobel Prize would evaporate. The cosmic web's filamentary structure results from dark matter's gravitational scaffolding. Ordinary matter flows along dark matter filaments, collecting in nodes where galaxies form. This cosmic architecture depends on the relative strengths of gravity and electromagnetic forces. Change light speed, and the balance shifts. Galaxies might spread uniformly through space or collapse into isolated islands with vast voids between them. Recent measurements of the Hubble constant, the universe's current expansion rate, disagree depending on measurement method. Observations of the cosmic microwave background suggest one value, while local measurements using supernovae suggest another higher value. This Hubble tension might indicate new physics. What if light speed has changed slightly over cosmic time? This could reconcile the measurements but would revolutionize cosmology. The stability of atoms in extreme environments provides another constraint on light speed. White dwarf stars compress matter to densities of tons per teaspoon. Neutron stars push even further, crushing atoms themselves. These objects exist only because quantum mechanics and relativity balance precisely at extreme densities. Change light speed, and white dwarfs might collapse immediately into black holes, or neutron stars might explode from degeneracy pressure. Cherenkov radiation, that beautiful blue glow in nuclear reactor pools, occurs when particles travel faster than light. In that medium, not faster than c in vacuum. This radiation is crucial for neutrino detectors and cosmic ray observations. The angle and intensity of Cherenkov light depend on the ratio between particle speed and light speed in the medium. Change c and every particle physics detector based on Cherenkov radiation would need recalibration or might stop working entirely. The possibility of variable light speed cosmology has been seriously proposed by physicists like João Magejo and Andreas Albrecht. They suggest light speed might have been much higher in the early universe, solving cosmological problems without inflation. But this requires rewriting fundamental physics. The conservation laws we hold sacred, energy, momentum, angular momentum, all relate to symmetries in space-time through Noether's theorem. Change light speed, and these conservation laws might fail. Quantum chromodynamics, the theory of the strong force, involves a running coupling constant that changes with energy scale. At extreme energies, quarks become nearly free, asymptotic freedom. This behavior depends on the relationship between strong force dynamics and the speed of quantum field fluctuations. Change light speed, and the strong force might not confine quarks into protons and neutrons. Matter as we know it couldn't exist. The vacuum catastrophe, perhaps physics' most embarrassing problem, highlights our incomplete understanding of light speed's role in nature. Quantum field theory predicts vacuum energy density about 10 to the power of 120 times larger than observed. This absurd discrepancy might involve light speed in ways we don't understand. If c could vary, vacuum energy might adjust itself, potentially solving the worst prediction in physics history. But this solution would create new problems, possibly making empty space unstable. Recent observations by the Dark Energy Survey have mapped millions of galaxies to understand cosmic acceleration. These maps reveal that dark energy behaves almost exactly like Einstein's cosmological constant, a fixed energy density of empty space. But this constancy depends on light speed being constant. If c varied over cosmic time, what we interpret as dark energy might be an illusion caused by changing physics. The universe's fate, eternal expansion, big rip, or eventual contraction, would be unknowable. The phenomenon of relativistic beaming shows how light speed affects what we observe. When objects move at significant fractions of c, their radiation becomes concentrated in their direction of motion like a searchlight beam. Quasars and gamma-ray bursts appear much brighter when pointed at us. Change light speed, and this beaming effect changes. Objects throughout the universe would brighten or dim. Some of the most energetic phenomena we observe might be ordinary events that happen to be beamed toward us. Let's explore how chemistry itself would unravel. Chemical reaction rates depend on electrons moving between atoms, governed by quantum mechanics and electromagnetic forces. The Arrhenius equation, which describes how temperature affects reaction rates, implicitly involves light speed through the energy barriers electrons must overcome. Change c and every chemical reaction in the universe would proceed at different rates. Slow reactions might become explosive, fast reactions might stop entirely. Your metabolism would fail within nanoseconds. The Unruh effect predicts that accelerating observers see empty space filled with warm radiation. This connects acceleration, temperature, and quantum fields through light speed. An astronaut accelerating at trillions of Gs would see empty space glowing like a furnace. Change c and the relationship between acceleration and perceived temperature shifts. Space travel might become impossible not due to engineering limits, but because acceleration itself would cook travelers with phantom radiation. Studies of millisecond pulsars, the universe's most precise clocks, have placed stringent limits on any variation in fundamental constants. PSR J04374715, spinning over 170 times per second, has been timed for decades with nanosecond precision. Any change in light speed would alter its spin rate through magnetic braking. We see no such changes constraining any C variation to less than parts per quadrillion per year. The universe's constants are eerily stable. The holographic principle suggests that all information in a volume can be encoded on its boundary, like a hologram. This principle, emerging from black hole physics and string theory, relates the maximum information content of space to its surface area divided by the Planck length squared. Light speed appears in defining the Planck length. Change c, and the universe's information capacity changes. Reality might become more or less detailed, like changing the resolution of a cosmic simulation. Observations of ancient supernovae in distant galaxies provide another test of light speed constancy. The light curves of type Ia supernovae, how they brighten and fade, depend on nuclear physics and radiation transport. These curves look identical whether we observe supernovae billions of light years away or in nearby galaxies. If light speed had changed over cosmic time, ancient supernovae would show different light curves. They don't, confirming C's stability across cosmic history. The quantum Zeno effect shows how observation affects quantum systems. Frequent measurements can freeze a quantum system, preventing it from evolving. This effect depends on the relationship between measurement time and system dynamics, ultimately involving light speed. Change c and the boundary between quantum and classical behavior shifts. Quantum effects might become macroscopic, or classical physics might invade the quantum realm. Schrödinger's cat might be definitively dead or alive, never both. Recent discoveries about time crystals, structures that repeat in time rather than space, reveal new phases of matter. These exotic states, created in laboratory quantum systems, challenge our understanding of thermodynamics and time itself. Their existence depends on precise relationships between energy, frequency, and quantum mechanics, all involving light speed. Change c and time crystals might become impossible or spontaneously form throughout the universe, creating temporal structures we can't imagine. The firewall paradox suggests that black hole event horizons might be surrounded by high-energy radiation walls that incinerate anything falling in. This paradox emerges from trying to reconcile general relativity with quantum mechanics, both theories where light speed plays fundamental roles. Change c and the paradox might resolve itself, or become even worse. Black holes might become naked singularities with no event horizons, exposing the universe to the physics-breaking infinities at their cores. Cosmic strings, hypothetical one-dimensional defects in space-time left over from the early universe, would create distinctive gravitational lensing signatures. These theoretical objects would be thinner than atoms but potentially light-years long, with mass comparable to mountain ranges per centimeter. Their formation and stability depend on phase transitions in the early universe involving light speed. Change c and cosmic strings might snap, releasing enormous energy, or proliferate until space becomes a tangled web of defects. The measurement problem in quantum mechanics, how and why quantum superpositions collapse into definite states, might involve light speed in subtle ways. Some interpretations suggest consciousness causes collapse. Others invoke gravity or spontaneous localization. The speed at which quantum information propagates and collapses depends on c. Change, light speed, and the quantum classical boundary shifts. Reality might become more quantum or more classical, affecting everything from computer chips to biological processes. Observations of the Lyman alpha forest, absorption lines from intergalactic hydrogen clouds, map matter distribution across billions of light-years. This cosmic web tracing depends on light from distant quasars passing through gas clouds at different distances and times. The pattern we observe assumes light speed has remained constant. Change c over cosmic time, and the apparent distribution of matter would be distorted. We might be fundamentally wrong about the universe's large-scale structure. The sonic black hole. Experiments where scientists create acoustic analogues of black holes in flowing fluids provide insight into how horizons form. Sound waves in these systems cannot escape regions where fluid flows faster than sound speed, mimicking how light cannot escape gravitational black holes. These experiments suggest horizon formation is a general phenomenon, not unique to gravity. Change light speed, and every type of horizon, gravitational, acoustic, even theoretical horizons in other fields, would shift position or disappear. The discovery of kilonovae, explosions from merging neutron stars that forge heavy elements, has revealed cosmic alchemy in action. The LIGO-Virgo detection of GW170817, accompanied by observations across the electromagnetic spectrum, showed gold, platinum, and uranium being created in real time. These element-forming processes depend on neutron capture rates, nuclear binding energies, and radiation pressure, all involving light speed. Change c, and the periodic table would be rewritten. Elements essential for technology and life might never form, or new, exotic elements might become stable. Let me share something that demonstrates just how finely balanced our universe is. The triple alpha process, which creates carbon in stellar cores, depends on a remarkable coincidence. Carbon-12 has an energy level at exactly the right position to allow 3 helium nuclei to fuse efficiently. This Hoyle resonance, predicted by Fred Hoyle, based on the Anthropic principle, involves electromagnetic and nuclear forces balanced through light speed, change c even slightly, and carbon formation fails. The universe would contain no carbon, no organic chemistry, no life as we know it. The edge of chaos theory in complex systems suggests that interesting phenomena emerge at the boundary between order and disorder. Life, consciousness, and complexity arise in this narrow zone. The physical constants, including light speed, place our universe precisely at this edge. Change c, and we might shift into either crystalline order where nothing interesting happens, or complete chaos where no structures can form. We exist in the Goldilocks zone, not just of our solar system, but of physics itself. Recent experiments with atomic interferometry have measured gravitational redshift with unprecedented precision. Atoms in superposition at different heights experience different gravitational time dilation, creating interference patterns when recombined. These quantum tests of general relativity confirm that gravity and quantum mechanics interact exactly as predicted when light speed has its observed value. Change c, and this delicate quantum gravitational dance fails. We might lose quantum mechanics, general relativity, or both. The black hole information paradox deepens when we consider the ER-EPR conjecture, which suggests that quantum entanglement and wormholes are the same phenomenon. This mind-bending idea connects quantum mechanics and general relativity through light speed. Change c, and the relationship between entanglement and space-time geometry shifts. Quantum computers might become impossible, or every particle pair might create traversable wormholes, turning space into Swiss cheese. Observations of ultra-high-energy cosmic rays reveal particles with energies that shouldn't exist. The GZK cutoff predicts that cosmic rays above certain energies should interact with cosmic microwave background photons, losing energy. But we observe particles beyond this limit. This might indicate new physics, or that light speed varies slightly at extreme energies. If c changes with energy, our entire framework of special relativity needs modification. The cosmological horizon problem becomes even more puzzling when we consider quantum entanglement. Regions of the cosmic microwave background that have never been in causal contact show identical temperatures to 1 part in 100,000. Inflation theory explains this by proposing rapid early expansion. But what if quantum entanglement, unlimited by light speed for correlations though not for information transfer, plays a role? Change c, and the relationship between entanglement and horizons shifts, potentially solving or worsening cosmological puzzles. Time loops and closed time-like curves, theoretically possible in general relativity under extreme conditions, depend critically on light speed. The Alcubierre drive, traversable wormholes and other exotic space-time geometries require negative energy densities that relate to light speed through quantum field theory. Change c and time travel might become possible with ordinary matter, or these exotic solutions might disappear entirely. Causality itself hangs on light speed's value. The emergence of classical physics from quantum mechanics, decoherence, happens when quantum systems interact with environments. The rate of decoherence depends on interaction strengths and information transfer speeds, ultimately limited by c, change light speed, and the quantum classical transition shifts. Macroscopic objects might maintain quantum superposition, or quantum effects might vanish even at atomic scales. The familiar world emerges from quantum mechanics only because light speed has its specific value. Recent observations of blazars by the MAGIC telescopes have detected TeV photons arriving simultaneously with lower energy radiation, despite traveling billions of light-years. This constrains any energy-dependent variation in light speed to incredibly tiny values. Some quantum gravity theories predict that space-time becomes foamy at the Planck scale, potentially causing high-energy photons to travel slightly slower. We see no such effect, suggesting space-time remains smooth even at the smallest scales. The false vacuum catastrophe scenario suggests our universe might not be in its lowest energy state. The Higgs field might be metastable, capable of transitioning to a lower energy configuration. This transition would propagate at light speed, destroying everything in its path. Change c and vacuum decay bubbles would expand faster or slower. A higher light speed might mean the universe should have already been destroyed. A lower speed might give civilizations time to detect and possibly escape approaching doom. Metamaterials with negative refractive index, created in laboratories, bend light backward and might enable invisibility cloaks. These materials manipulate electromagnetic waves in ways that seem to violate common sense, but not physics. Their properties depend on structures smaller than light's wavelength, ultimately constrained by c, change light speed, and metamaterial properties would shift. Technologies we're just beginning to explore might become impossible or trivially easy. The quantum vacuum isn't empty, but seethes with virtual particles and quantum fluctuations. The dynamical Casimir effect, where moving mirrors create real photons from vacuum fluctuations, has been demonstrated experimentally. This conversion of virtual to real particles depends on acceleration relative to light speed. Change c and the vacuum might become either more or less active. Empty space could spontaneously generate matter or become truly empty, destroying quantum mechanics itself. Observations of galaxy rotation curves, which led to dark matter's discovery, assume light speed determines how electromagnetic forces bind visible matter. If c varied across cosmic distances or times, what we interpret as missing dark matter might be variations in electromagnetic force strength. The bullet cluster, where dark and ordinary matter separated during galactic collision, provides evidence against this, but subtle AC variations could still affect our cosmic inventory. The principle of least action, one of physics' most beautiful ideas, states that nature follows paths that minimize or extremize action. Light travels in straight lines because that minimizes travel time. Planets orbit in ellipses because that extremizes action. This principle, which underlies all modern physics, defines action using light speed. Change c and nature's optimization criterion changes. Particles might follow completely different trajectories. The elegant mathematical structure underlying physics would crumble. The quantum eraser experiment reveals something profound about reality and time. By manipulating entangled photons, scientists can seemingly change the past, erasing or restoring interference patterns after photons have already been detected. This temporal paradox is resolved through careful analysis of when information becomes available, all governed by light speed limits. Change c and the boundaries between past, present, and future blur further. We might gain actual retroactive control over quantum events or lose the ability to define temporal sequence at all. Recent discoveries about quantum scarring show that even chaotic quantum systems can display unexpected order. Certain trajectories in quantum chaos become enhanced, like scars on the quantum landscape. These patterns emerge from interference between quantum paths, with phases accumulating at rates determined by action divided by Planck's constant, ultimately involving light speed. Change c and these quantum scars would shift, potentially destroying the delicate balance between quantum chaos and hidden order that might underlie everything from atomic stability to consciousness. The cosmic neutrino background, those ghostly particles from the universe's first second, carries information about physics at energies we can't recreate. These relic neutrinos have been cooling for 13.8 billion years. Now, with energies so low, we can't detect them directly, but their gravitational effects on cosmic structure depend on their mass and speed relative to light. Change c in the early universe and these cosmic ghosts would tell a different story, potentially revealing or concealing crucial information about the Big Bang. Let's examine what happens at the Planck scale, where quantum mechanics and gravity merge. The Planck length, about 10 to the minus 35 meters, is built from gravity's constant, Planck's constant, and light speed. Below this scale, space itself might become quantum foam, with virtual black holes popping into existence. Change c and the Planck scale shifts. Quantum gravity effects might become visible at larger scales, or space might remain smooth down to infinitely small distances. The texture of reality itself depends on light speed's value. The bootstrap paradox in physics suggests that consistency requirements alone might determine the laws of nature. String theory embodies this idea. The requirement that quantum mechanics and relativity coexist constrains the universe to specific dimensions and particle spectra. Light speed enters these consistency conditions fundamentally. Change c, and the mathematical requirements for consistent physics change. We might need different dimensions of space, different fundamental particles, or find that no consistent theory exists at all. Observations by the Alpha Magnetic Spectrometer on the International Space Station have detected an excess of high-energy positrons, possibly from dark matter annihilation. The energy spectrum of these antimatter particles depends on how they propagate through galactic magnetic fields at speeds approaching c. Change light speed, and dark matter signatures would shift. We might suddenly detect dark matter everywhere or lose all indirect evidence for its existence. The quantum Hall effect, where electrical resistance becomes quantized in two-dimensional systems, reveals deep connections between topology, quantum mechanics, and electromagnetism. The resistance plateaus occur at precise fractions involving fundamental constants, including light speed. This effect, which earned multiple Nobel Prizes, shows that C isn't just about motion, it's woven into the quantum fabric of matter. Change light speed, and these topological states might vanish, taking with them our understanding of quantum phases and potentially quantum computing architectures. Recent gravitational lensing observations of colliding galaxy clusters have mapped dark matter with unprecedented precision. The separation between dark matter and hot gas during these cosmic crashes depends on their different interactions. Dark matter feels only gravity, while gas experiences electromagnetic forces too. This separation rate involves the ratio between gravitational and electromagnetic coupling, ultimately depending on c. Change light speed, and dark matter might become visible, or ordinary matter might become dark. The possibility of Boltzmann brains, conscious entities arising from random fluctuations, becomes more or less likely depending on light speed. In an infinite universe, random quantum fluctuations will eventually create anything, including functioning brains. The rate of such fluctuations depends on vacuum energy and quantum mechanics, both involving c. Change light speed, and Boltzmann brains might outnumber evolved beings, calling into question whether we're real or random fluctuations ourselves. Time crystals challenge our understanding of thermodynamics by showing that perpetual motion is possible in quantum systems. These structures repeat in time without energy input, seemingly violating basic physics principles. Their existence depends on precise relationships between interaction strengths and driving frequencies, ultimately constrained by light speed. Change c, and time crystals might become impossible, or all matter might spontaneously form temporal structures, creating a universe where everything pulses in complex rhythms. The cosmic web's filamentary structure isn't just beautiful, it's optimal. Computer simulations show that dark matter naturally forms a web that minimizes gravitational potential energy while maximizing connectivity. This optimization depends on the balance between expansion and gravitational attraction, involving light speed through both relativistic effects and structure formation rates. Change c, and the universe might organize differently, perhaps into isolated bubbles, uniform fog, or unimaginable geometries. Quantum biology discoveries show that life exploits quantum mechanics in unexpected ways. Photosynthesis uses quantum coherence to efficiently channel energy. Bird navigation might use quantum entanglement to sense magnetic fields. These biological quantum phenomena exist at warm temperatures where decoherence should destroy them instantly. They work only because of precise tuning of interaction strengths and timescales, ultimately depending on c. Change light speed, and life's quantum tricks might fail, possibly making complex life impossible. The measurement of gravitational waves has opened an entirely new window on the universe. LIGO and Virgo detect space-time distortions smaller than atomic nuclei, revealing black hole mergers billions of light-years away. These measurements confirm that gravitational waves travel at exactly light speed, as Einstein predicted. Change c and gravitational astronomy would need complete recalibration. Worse, if gravitational and electromagnetic waves traveled at different speeds, causality paradoxes could tear apart the logical structure of spacetime. Recent studies of quantum error correction show that nature might inherently protect information. Topological quantum states can store information immune to local perturbations. This robustness emerges from global properties that depend on the relationship between energy scales and interaction speeds. Change light speed, and nature's error correction might fail or become so strong that evolution and change become impossible. The universe's ability to compute its own future depends critically on c. The dark energy equation of state parameter, W, determines the universe's ultimate fate. Current measurements suggest W is very close to -1, consistent with a cosmological constant. But this parameter relates energy density to pressure involving light speed through relativity. Change c and dark energy's nature changes. The universe might recollapse, tear apart, or do something we haven't imagined. Our cosmic destiny hangs on light speed's value. As we approach the end of this cosmic journey, let's confront the ultimate question: why is light speed what it is? Why 299,792.458 kilometers per second and not some other value? The answer might be the most profound in all of physics, because we're here to ask the question. This isn't mysticism, it's the anthropic principle backed by hard mathematics. Studies by physicists like Martin Rees have identified about 30 fundamental constants that, if changed by even tiny amounts, would create sterile universes. Light speed sits at the center of this cosmic conspiracy. It's not just one constant among many, it's the keystone that holds all others in place. Remove it, and the entire arch of physics collapses. The multiverse hypothesis suggests our universe might be one of countless others, each with different fundamental constants. In this cosmic lottery, most universes are stillborn, their physics incompatible with complexity. Only in universes where constants like light speed take very specific values can atoms form, stars shine, and life evolve. We find ourselves in such a universe not by design but by necessity. Dead universes have no observers to wonder why they're dead. Recent observations by the Dark Energy Spectroscopic Instrument are creating the largest 3D map of the universe ever made, measuring millions of galaxies to understand dark energy's nature. These measurements assume light speed has remained constant across cosmic time and space. If c varied even slightly, these cosmic surveys would be mapping illusions. Every conclusion about dark energy, cosmic acceleration, and the universe's fate would be wrong. The quantum suicide thought experiment pushes the anthropic principle to its logical extreme. If many worlds' interpretation is correct, consciousness only continues in branches where the observer survives. Extended to cosmology, we might only find ourselves in universes where physics allows observers. Change light speed, and those alternate universes might exist but have no one to experience them. Our universe's constants might be selected not by physics but by the requirement of consciousness. Let's consider what changing light speed would mean for information itself. Shannon's information theory shows that channel capacity depends on bandwidth and signal-to-noise ratio. In physics, the ultimate information channel is space-time itself, with capacity limited by the Planck scale and light speed. Change c and the universe's information carrying capacity changes. Reality might become more or less detailed, like changing the resolution of existence itself. The holographic bound suggests that the maximum information in any region equals its surface area in Planck units. This profound limit, emerging from black hole thermodynamics, means the universe might be fundamentally two-dimensional, with the third dimension emerging from information relationships. Light speed appears in defining both Planck length and how information propagates. Change c and the universe might have different effective dimensions or information density. Recent quantum supremacy experiments by Google and others have shown that quantum computers can solve certain problems exponentially faster than classical computers. But quantum computation's power depends on maintaining coherence while performing operations, a balance involving light speed through decoherence rates. Change c and quantum computers might become impossibly powerful or completely useless. The computational capacity of the universe itself would shift. The cosmic censorship hypothesis suggests that nature abhors naked singularities, regions where physics breaks down visibly. Black holes hide their singularities behind event horizons, protecting the universe from their law-breaking cores. These horizons exist where escape velocity equals light speed. Change c and horizons shift or disappear. Singularities might be exposed, spreading regions where physics fails. The universe protects itself through light speed's specific value. Observations of time dilation in cosmic ray muons provide daily confirmation of special relativity. These particles, created when cosmic rays hit Earth's atmosphere, shouldn't reach the ground before decaying, but time dilation at near light speed gives them enough time from our perspective. This effect, verified millions of times in particle detectors worldwide, depends precisely on light speed's value. Change c and this delicate relativistic dance fails. The possibility of vacuum decay, our universe transitioning to a lower energy state, depends critically on quantum tunneling rates. These rates involve barrier heights and widths measured in units built from light speed. Change c, and vacuum stability changes. A slightly faster light speed might mean our vacuum should have decayed billions of years ago. A slower speed might make our vacuum absolutely stable, freezing the universe's evolution. String theory's landscape problem suggests there might be 10 to the 500 different possible universes, each with different physics. Light speed variations would create different landscapes entirely. The anthropic principle becomes almost inevitable. With so many possibilities, some must allow observers. But this raises deep questions. Is physics ultimately about mathematical consistency or observership? Does the universe exist independently of consciousness, or are they inseparable? As we near the end of our journey, consider this. Every atom in your body, every photon you see, every thought you think depends on light speed being exactly what it is. You are not separate from the universe. You are the universe understanding itself. The specific value of c isn't a cosmic accident, but a requirement for cosmic self-awareness. The James Webb Space Telescope continues to revolutionize our understanding, recently detecting galaxies that formed earlier than thought possible. These observations push the boundaries of when stars first ignited, when heavy elements formed, when the conditions for life became possible. All these cosmic milestones depend on light speed's value. Change c and the universe's biography rewrites itself. Recent philosophical work on the hard problem of consciousness suggests that experience itself might be fundamental, like mass or charge. If consciousness is basic to reality, then the universe's constants might be selected by the requirement of experience, not just existence. Light speed would be what it is because that's what allows the universe to experience itself through beings like us. The simulation hypothesis proposes our universe might be computed rather than fundamental. If true, light speed might be the maximum information propagation rate in the underlying computational substrate. Change c and you'd need different computing architecture. The universe's speed limit might reflect not physical law, but computational constraint. As we conclude this cosmic exploration, remember that we've touched on just a fraction of light speed's importance. Every equation in physics, every process in nature, Every moment of existence depends on C having its precise value. The universe isn't just fine-tuned, it's impossibly, miraculously, perfectly tuned. Look up at the stars tonight with new appreciation. Those points of light are not just distant suns, but proof of cosmic stability. Their light, traveling for years at exactly C, carries the message that physics works the same across space and time. In a universe where light speed could change, there might be no stars, no planets, no life, no consciousness to appreciate the cosmic drama. We are stardust, yes, but more than that, we are the universe's way of understanding why it exists. Light speed isn't just a number. It's the cosmic constant that makes constants possible, the universal speed that makes the universe possible, the finite value that makes infinity comprehensible. The next time you turn on a light, remember, you're not just illuminating a room, you're participating in the fundamental process that makes existence possible. Every photon travels at the only speed that allows atoms, stars, planets, and people to exist. We live in the one universe among potentially infinite possibilities where consciousness can emerge and ask, why is light speed what it is? The answer, in the end, is simple. Because we're here to ask the question. And that's the most profound answer in all of science. If you made this far, make sure to subscribe to the channel and give a thumbs up. Your support means a lot to me. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. Does time stop when you hit the speed of light? In this video, discover the real science behind time dilation, Einstein's special relativity, and what happens to time as you approach light speed. See you there.